Swayam Prabha. Digital India. Educated India.
So welcome back. In the last lecture we were looking at tunable metasurfaces, and those are as we said very important for realizing tunable functionalities. In addition, we'll also look at another important class of metamaterials called as active metamaterials. So the word active in this context, I mean that where they have some optical gain. So in general, the devices we have seen so far are passive structures. That is, they do not add energy. So they just take the incoming energy. Some of it is going to be redirected, some of it is going to be absorbed, but they're never going to add energy to the incoming beam. Now in this lectures and subsequent lectures this week, I will talk about these active metamaterials, okay, which essentially have the feature of optical gain, which enhances the input signal and amplifies it. Okay, so we have seen the amplifiers, right? In the case of electronics, we understand how they work. They take energy from the pump or the source, and then they add that energy. The incoming signal gets amplified. That's what we see in the electronic devices. A similar thing happens in the case of optical devices. Okay, we'll look at that. Before I get into those details, I just want to quickly mention about the radiative processes that occur in a system. So this the theory for this was given by Einstein back in 1916 or so. So he looked at how light interacts with materials, and then he came up with this model of two-level system and the coefficients associated with that. So to understand what this is, let's look at what we will call as a two-level system. Okay, that's what I'm showing here. So I can think of so basically let's look at a two-level system. So I have the ground state, or I'll call this as state number 1, and the number of atoms in that state I'll call as N1. Similarly, I can have an excited state. I'll call this as 2, and then the number of atoms in an excited state is 2. Okay, so under normal conditions, we say that the system will exist in a thermodynamic equilibrium, and there is a specific rate of the ratio of atoms that are present. For example, if I look at N2 divided by N1, the ratio of the atoms in the excited state to the ground state, this ratio will be given by Boltzmann distribution, and it will be E2 minus E1 by KT. Okay, so okay, let me just do it cleanly. So where my E2 and E1 are the excited state and the ground state. So it has a population N1 and the energy level, let's say, E1, and the excited state N2 and energy level E2. Okay, so you have this distribution of population. So in general, what we'll expect is the higher state will have lesser number of atoms. That's the basic phenomena. Okay, that we'll see. This is in thermodynamic equilibrium. All right. So Einstein looked at what happens when you have, let's say, and photon incidents on such a system. Okay, so in this case, the question was what are these excited and ground states? Okay, they can be anything. For example, if you're looking at a semiconductor, they can be the valence band and the conduction band. So essentially, you have a few electrons in the valence band, and the conduction band is empty in intrinsic semiconductor case. But then you can have a situation where there are holes in the valence band and then electrons in the conduction band. That can be one sort of a situation where there is a non-equilibrium situation created. Or you could also think of just the particle in a box problem, right? If you, let's say, confine, you create a system like a quantum well, and then you have these energy levels. Those energy levels can be these states. Okay, so it's not necessary that there are two-level system is an approximation. Okay, this is what we will call as a two-level system. This is a two-level system. Okay, it by no means means that there are only two levels in the material that we're considering. For example, in a quantum well, there is n equal to 1, 2, 3, and so on. You can have transitions happening between any two states. So we usually talked about the absorption process when the electron gets excited from the lower state to the higher state. But for some reason, there is a population, the electron in the excited state that can emit back. It can emit from, let's say, 3 to 2 or 3 to 1 and so on, right? So we have the associated selection rules. We said that whenever delta n is 1, it is valid, or it's a allowed state, and delta n equal to 2, it's not allowed, even number, right? So that sort of a states can be there. It need not be, it's a general model. Anywhere an electron is making a transition from the excited to the ground state. It's a two-level system, okay? Does that answer? Okay, all right. So now, Einstein looked at this sort of a process where, you have this excited and ground states, and then he asked the question, what happens when light is incident on this? Okay. Of course, when light is incident, we all understand that the population changes. So I can look at the rate at which the population of, let's say, the ground state is changing. So I will write dN1 divided by dt. Okay. That means the rate at which the population in the ground state is changing with time. And what does that depend on? One of the factors that depends on is the number of atoms available in the ground state, right? So that way, this is going to be equal to, let's say, N1, because if there are no atoms available in the ground state, there is no excitation possible, right? So that's one thing. And then it is also going to depend on the intensity or the distribution, the radiation profile of the spectral density of the incident light. So that we will call as rho. Okay, rho of nu, essentially I'm calling that. So that represents at each wavelength or a frequency, what are the number of photons that are incident. If it's a monochromatic wave, it's simply a sharp line with the number of photons that we can calculate. Okay, so it's going to depend on that. If you have larger number of photons incoming, then you can have more number of electrons that are excited. So that's the spectral density, right? So I'll call this as, this is a spectral density. Okay, so it's basically the number of photons essentially, okay, per, whatever. So now, what else? So there is also a finite probability of this transition happening, and Einstein gave this a name, and he said that he called it a B coefficient. So let me just stretch it a little bit. Okay, so Einstein said this is going to depend on, he gave a coefficient B1, 2. Okay, so while making a transition from first level to the second level, there's a probability associated with it. Okay, and that he called as Einstein B coefficient. So this is Einstein's B coefficient. Okay, and of course there's a negative sign, because as you have more and more photons incident, the population of N2 or N1 reduces, so there should be minus here. So this is the first equation that happens when you have absorption process. So essentially, a photon is exciting an electron from the ground state to the excited state. Now, you can have another scenario wherein, let's say, an electron is already present in the excited state somehow. Now, that electron can actually emit a photon and come down. In the first case, we have absorption of photons. In the second case, I can have an emission of photons, and it doesn't need any impedance. So we call it a spontaneous emission process, wherein it just automatically releases a photon and then comes down. The electron will actually make a transition from the, let's say, the excited state to the ground state. So initially the electron was here. Electron in E2, energy level E2. Finally, the electron will be, after transition, finally electron is in E1, right, energy level 1. So this sort of a situation can happen. Now what does that depend on? So this depends on, if I can write a similar equation now. So I can write dN2 now. Okay, basically how is the population of N2 changing, or I can even write dN1, there's no problem, dN1 by dt, let me take. If I have that, so what is that depending on? Now for this particular emission process, again, the population, the rate of change of population in N2 is going, N1 is going to depend on the number of, to make my life simple, let me still keep it N2 only, okay, N2 divided by dt. That's going to depend on N2. So if you have more and more electrons, more atoms in the excited state, then they'll have more probability of emission. And then there is a probability of emission, which is spontaneous emission. So Einstein gave a name A21. Okay. So this is A21 is the probability of spontaneous emission. So this is a second process that can happen. And then in addition, what is unique is Einstein looked at the various thermodynamic arguments, and he came up with a third process which he called as stimulated emission that should exist. Okay, the interesting thing about stimulated emission is that if you have a situation as before, now you have an atom in the excited state. Now if you don't have any other photon incident, it just emits spontaneously. But suppose there's a case where there's a photon which is incident. Now this incident photon can stimulate an electron to make a transition from the excited to ground state, and then cause an emission of a second photon. So initially you had one photon incident, and now when coming out you have two photons which are coming out. Okay, so this process Einstein called it a stimulated emission. The nice thing about the stimulated emission process is that the second photon, okay, the emitted photon has the same polarization phase as the phase and frequency as the incident photon. This is a unique feature that is usually not there. Okay, so this stimulated emission process is what Einstein discovered, and he said that okay, the rate of change of energy level 2 is going to be, now there's going to be N2 that is there. And this sort of a process, of course, because you have an incident photon, that should depend on the rho. Rho of nu is basically the same spectral density that we came across before. And now there's a decrease which is basically stimulated emission process. He called it as B21, sorry. Okay, and there's a negative sign because it reduces the population. So this is the stimulated emission coefficient. Okay, probability. Alright. So these are the three processes. Have an incident light, and that's why you see the B coefficient here is, you can think, we call it absorption, but it's stimulated absorption if you want to call it. Okay. So these two are opposite processes. There's a spontaneous emission. Can you have spontaneous absorption? Right? Can we have spontaneous absorption? Well, we can't. The reason is, how will, absorption means an electron has to go from lower level to the higher level. Right? How will it spontaneously grow from lower level to the higher level? It requires some energy that comes in from somewhere. So you don't have a spontaneous absorption process. All right. So Einstein considered these three processes, and then he applied what is known as principle of detailed balance, and then he essentially applied that, and he figured out that the coefficients themselves are not independent. So I just summarized whatever I had written on the previous slide. So essentially the same expressions here. So the rate equations, you basically consider an equilibrium situation where there is no change of population. So you dN by dt, you make it 0, and then you look at the relations between the various processes, and the spectral density has to be in the form of Planck's distribution. If you apply that, you will see that the coefficients are related to each other. So for example, here the spontaneous emission coefficient A21 is going to be related to B21 using a factor here, and then the absorption and the stimulated emission parameters are equal to each other. And there's an additional G and G1 and G2 which are known as the degeneracy factors. For now, you can just consider them to be 1. Just assume that that's a simplified life. So absorption and stimulated emission are opposite to each other. They're equal in rate. And the spontaneous emission process actually depends on the stimulated emission, but then there's a product of, there's some coefficient associated with that. And this is a very important thing. If you notice, the spontaneous emission depends on the stimulated emission, but then there is this frequency cube term that comes in. That means that as you try to, if you try to have higher and higher frequencies, for example, compared to, let's say, red frequencies, I look at blue frequencies. Blue has a higher frequency. That means at higher frequencies, the stimulated emission is much more dominant than at red frequencies. And that is why it turns out it's quite challenging to build a blue laser. Red laser is easier to build, but as you go to higher and higher frequencies, the spontaneous emission process dominates. And spontaneous emission essentially means the photon is emitted in some random direction. Okay, so that's not something that we prefer usually. Anyway, we will talk in more detail when I discuss the lasing part. But yeah, so I wanted to bring to your attention that these coefficients are very important whenever we discuss any active materials where there is gain involved. Einstein coefficients play an important role. And what are the units of Einstein coefficients? Can you look at that? So for example here, these coefficients are essentially, you have n by t, number of atoms divided by t, right? And the density is, it's just a shape, right? You have, so this units has to be 1 over time. Okay, the spontaneous emission is 1 over time. And then B21, what is the energy density units? We'll also have, okay, yeah, so B21 can have a slightly more complex, this one. Let me not do this. So we will have to come back and talk about it. A21 is easy. A21 is simply 1 over time. B21 and B12 will also have to consider what are the units of the spectral density. Okay. And then, or you look at this term, h nu cube by c cube. Okay. So h has a unit, you can compute what is nu by c units and you can figure it out. Okay. All right. So now, okay, the question was in the spontaneous emission when we were talking about, we don't consider any spectral density. The reason is that there is nothing that is required for the emission process to happen. Okay. Without any incident field, it can actually emit. It turns out that it's a little bit subtle. Right now we are not considering, but if you look at the full quantum description, later on we'll talk about quantum optics, wherein even if you don't have any photon, there's never a possibility that there's no photon. There is always what is called as vacuum field fluctuations that come in. We will discuss about that in the 10th week of the course. That's an interesting part of what happens. So that's a very, very small fluctuations that are there all throughout the space. There's never a situation that there is nothing. And then in that case, you have that vacuum field which actually causes the emission of a photon. And yeah, this is a different interpretation. We'll look at that later on. But in general, in the bulk, I mean, in this case, we don't have any incident photon and you have emission of, let's say, a photon that is coming in, right? There's no incident photon. So we call it spontaneous emission. There's no need of any spectral density. When you have an incident field, then you have to talk of the distribution of the field. Like in the case of absorption, we looked at, at what wavelength and what density and all that will come into picture. In the case of stimulated emission also, what is the stimulating field? It becomes important. But in absorption, there is nothing that is exciting that, no? Spontaneous emission, there's nothing. So we don't put any field. All right. Okay. The question was, you said that the emission, the two photons in the stimulated emission have the same phase and, the wavelength and all that, right? Why is that? Why is that happening? So you can, one way of thinking about it is this. We saw that any material response, anytime a photon is incident on a material, it excites an oscillator, right? It's a dipole that excites. You have basically, let's say electric field is driving the electrons back and forth. It may be a bound oscillator, but whatever, the Lorentz model described that you have this oscillation that's happening. Now, and then that oscillation, the oscillation of the charge causes emission of light, the secondary light. That's a photon that is getting emitted. So you can think of this process as something that, you have a particular state in which the scattered intensity, or the scattered intensity is what I'm calling as an emitted photon. The scattered intensity essentially has to have the same frequency because the incident frequency is driving it. That's nothing else. And also it is in phase with the incident photon. So the dipole oscillator is in phase. The emission from the dipole oscillator is in phase with the incident photon. That's when you can have coherent emission. In general, you'll see that there is this, there's a phase lag and there's an amplitude of scattering and all that, right? Now, in this case, you're having a single photon that is getting emitted with the same frequency and phase. That's why they're coherent. And that actually is fundamental to the concept of laser that we will discuss shortly. Yeah. Okay. I hope, it's a little bit of a counterintuitive thing that, suddenly why is the photon having the same phase? The important thing is how many photons are getting emitted in that. So it's an important factor to consider. Let's say you have a situation that, both the spontaneous emission and stimulated emission process have an electron in the higher state, right? And then they're emitting. So what is the ratio of spontaneous emission photons and stimulated emission photons? What will be the ratio? The coefficient, right? A21 by B21. And that is going to be a large number. If I look at the ratio here, A21 divided by B21, this is the coefficient. And this is terahertz, okay, and this is C cube. It's a number, right? And spontaneous emission is going to dominate stimulated emission usually. So in general, you can't observe lasing. It's not an easy thing to observe lasing. We have to create a specific set of circumstances to observe lasing. Okay, we'll talk about that in a moment. All right. So this is the basic processes. All right. Now, so essentially, an example of this sort of a two-level system, I think because of the question I answered, and then we looked at the system already. We had conduction band and the valence band, and we said that if you're having a situation where electrons are in the conduction band and holes in the valence band, you can have a recombination of electron hole pairs and generating photon. And we introduced the idea of optical gain and so on. So this is how this gain can be related. Now, this is not a single energy level, right? We understand that these are range of energies, and these are range of energies in the conduction and valence bands. But I can think of the emission as, where the maximum probability, maximum carrier density happens. We can think of the emission as between two levels. Okay, we are just modeling it that way. In reality, it is going to be a range of levels, each of them a two level, right? Each set of two energy levels can be one transition. So that's why you'll have a broad emission. So if you remember, this was the, we talked about this. We will again revisit this. That's why I just wanted to bring your attention. We talked about this in the second week, I believe. So in the next lecture, I want to actually talk about, why this is important. We will discuss a little bit more details about this. And then we also saw that, in this case, you have this emission that happens. We also mentioned this. You can have photoluminescence or electroluminescence. Essentially, you can excite an electron to go into the atom to go into higher state by electrical means or optical means. Okay. Once you excite, you have an emission happening, and there's this characteristic lifetime that happens that, is observed. And this lifetime is very important. Why do we call it a lifetime? What is the average duration? It's a duration for which an atom stays in the higher state. So for example, here I could write a term and say that my population N2 of time t is going to depend on some initial state, N2 of 0, at times 0, there is a population N2, and then there is going to be an exponential decay minus t by tau to 1. Okay, what is this tau 2? This tau to 1 is a lifetime of the higher state. When I have two states, I can even say tau 2, but in this case anyway there are two, so I don't mind. Okay, so tau to 1, it essentially becomes 1 over the radiative time plus 1 over the non-radiative time. Okay, so this is how overall lifetime of the excited state behaves. So if you have strong non-radiative decay, that means electrons are getting de-excited into photons and so on, then it's not a very good material for emission of light. Okay, non-radiative recombination plays an important role. We'll revisit this again this week. All right. So because of that, you see this emission. Okay, we would prefer the light to be emitted in the radiative way. Okay. So you see, even though we are modeling it as a two-level system, in reality there are range of wavelengths that are emitted here. You see here, it's not a single line. You will see single lines in the case of atomic systems. If you remember this 11th standard, you have studied about Lyman, Balmer series, Paschen series, and so on, which are essentially very sharp lines that come in when you study excited gases. The reason they are sharp is that, okay, this is single levels. Of course, in a sodium vapor, there are going to be multiple levels, but one particular level in that is going to correspond to one particular wavelength, and that's what was studied, and people understood how the atomic structure behaves. Right? A lot of analysis of atomic structure happened because of these ideas. All right. So so this is about the lifetime. I just wanted to mention this because it's important in understanding the subsequent part of this this week's content. All right. So this brings me to the last part that I just want to discuss in this lecture. That is the laser. Okay, a laser is an important modern device. We are all familiar with transistors, but all our communication that we see is because of lasers. Okay, we cannot emphasize this enough, because without lasers, there is no long distance communication. That means there is no internet, there is no data, nothing. Okay, all of that, the backbone is a laser, semiconductor laser. So I just want to quickly talk about just the fundamental principles, and then we will actually talk about how to miniaturize these things, which is an important part of what is happening currently in the research community, and also in my group. We are working on this, so we will talk about some aspects of that work. So we are all familiar with, I hope you are familiar with the traditional idea of laser. So essentially it is an oscillator, and laser, the expansion is light amplification by stimulated emission of radiation. That was the expansion of laser. Initially it was an acronym, but now it's simply people use it as a word. So what it has is two mirrors like this. Take two mirrors, and then you put a gain medium. Gain medium is like, the two-level system or excited semiconductor, whatever. You put a gain medium which is actually having gain, not loss. Okay, so we are pumping the by default, if you look at any material, it's never going to have gain, because we said the distribution of atoms is going to follow the Boltzmann distribution. So excited state will always have lesser number of carriers than the ground state. So you will only have absorption, which is probable. But I have to create a situation, we will talk about that, we call it a population inversion. Only in that scenario you will have gain. So you have this gain medium, and then the photon actually goes back and forth between these two mirrors. As it goes through the gain medium, each time it gets amplified. One photon will generate second photon. The two photons will generate 4 photons. 4 photons will generate 8 photons, and so on. So it's like a chain reaction which quickly builds up the intensity of photons at one single wavelength. So that is the important role. So for a laser to operate, we say there are 3 main features. One is gain is essential, gain medium. Second one is we should have a cavity. And the third important thing is population inversion. I'll talk a little bit more of details in this population inversion. The first part is the gain medium. We've understood that. The cavity is basically what is shown here. Let's say 2 mirrors. Okay, why are 2 mirrors important? Well, think about a very simple case. Let's say I have a mirror which has 1% transmission. Okay, so I'll consider one mirror like this, and I shine photons from this side, and it has 1% transmission. So if there are, let's say 10,000 photons that are incident on this, if I have 1% transmission, the number of that photons that come out of this side should be 100 photons. 100 photons, right? Now I'll put another mirror. So what I'm saying is a laser is simply 2 mirrors, right? So I'll put another mirror here, mirror 2. This is M1, this is M2. If you have 100 photons incident on it, then what happens? You'll end up with 1% transmission. So I'll be ending up with 1 photon here, right? If you simply take the without any gain medium and you have simple intensity, then quickly you'll see that the number of photons is actually not very large. Okay, the number of photons that come out is very, very small. In effect, that overall transmission will be 10 power minus 4. But now, if I put a gain medium, I also amplify these photons, and I'll also specifically amplify particular frequencies. The cavity, in a way, selects a particular frequency in such a way that my transmission will be 1. The transmission coefficient of the entire cavity will be in such a way that there is a lot of analysis, and maybe it's a little bit more of detail than what you need. But if you look at the transmission coefficient in this cavity, it will show sharp spikes like this. At particular wavelengths, you essentially have a lot of gain, and there is a constructive feedback. Okay, the incoming, so you have a photon that is going in, it's emitting a second photon, and then it comes back. Okay, and again introduces another set of photons. If they are in phase, you can have constructive addition of all these photons and you get large intensities. But if they're not in phase, then you will have destructive interference and you don't have any photons that are coming out. So because of that, at particular frequencies or wavelengths, you have these sharp peaks that come in because of the cavity, and that's an important part of a laser. And you can study a little bit. These are called as Fabry-Perot cavity. You can study more details if you're interested. So, but yeah, it causes amplification. Okay, at that particular frequencies, you have amplification happening. So the cavity is designed this way. And how are you starting the lasing oscillation? It's like an oscillator. You never need to start an oscillator, right? You just, out of noise, an electronic device can actually generate a signal. Similarly, in this case, you have a power supply, you have a large gain medium, and then you feed it back. So you'll see that out of noise, there is some variation in the electrical signals or in the optical signals, and eventually you get a very pure sine wave, a monochromatic output, which is known as a lasing. Okay. You have seen a laser always. Already if you've seen a laser pointer, there is this beam that really goes very, in a straight direction, right? Without bending. That's a laser. It's very distinct from what you see from a light. In a normal light, like an LED light that you have in your home, the light is never going to go in that straight line. It keeps spreading in different ways, right? In different directions. It spreads everywhere. It's not like a beam, a single beam. Whereas a laser is actually, it goes large distances without bending. And that is a unique property of laser that is, useful in communications. All right. So yeah, so we will talk a little bit more about it. And the last thing important in a laser is what we call as a population inversion. Okay. I'm just reviewing these ideas because these things are, I'll use them when I talk about nanoscale light emission. So I just wanted to introduce them. So for example, here we talked about the two-level system. Let's say N1 and N2. And we said that there is a Boltzmann distribution that is always there. So N2 by N1 equal to exponential minus E2 minus E1 by KT, right? So always the N2 is going to, in general, N2 is less than N1, right? So absorption is dominant. Okay. When is emission dominant? Whenever you have larger number of atoms in the excited state. For emission, N2 should be greater than N1. Then you have emission. When I showed you the photoluminescence data, we created N2 to be greater than N1 by pumping it. But we have just shined high energy beam so that electron goes into higher level. It kind of undergoes thermal relaxation and comes down to the band edge and emits a photon. That's what we talked about, right? It can be pumped optically or even electrically. I can supply electron hole pairs by I'll show you in a moment how we can do that. So you can have N2 to be greater than N1. That is essential, okay? And this phenomena of N2 being greater than N1 is known as population inversion. This is an essential part of laser. If you don't have population inversion, you cannot have lasing, right? You cannot have emission, stimulated emission essentially. Otherwise, spontaneous emission is strong and then there's nothing much that happens. Once you have N2 greater than N1, stimulated emission takes over. And how strong is, if let's say you have a stimulated population inversion of, let's say 100. Okay, I'm just taking an example. Let's say initially there are 100 photons in the excited state, N2, 100 N2 and 0 N1. Now, one photon will be created. One photon will be created and then the population inversion reduces to 98 because 99 minus 1. So 98. Again, another photon again reduces, 2 for 96 and so on. So very quickly as the photon is emitted, the population inversion reduces. It's never going to be fixed, right? So continuously we have to keep pumping the medium to maintain population inversion. If you don't maintain population inversion, you lose. You don't have lasing, okay? So in this context, it turns out that the simple two-level system is not really a great system for lasing. The reason is, if you have just two levels, at some point there's going to be equilibrium between the absorption and emission processes. Okay, so let's say you created population inversion at perfect population inversion, N2 equal to 100 and then N1 equal to 0, and then you have emission. But quickly, the N1 population increases, so absorption increases. So N1 to N2 again. So there's an equilibrium that will quickly come down between N1 and N2. Under some conditions, it might even happen that there is equal distribution of N1 and N2. Okay, so it's never an efficient system for lasing. So to create lasing, scientists use what are known as 3-level and 4-level systems. Typically what happens in this case is, instead of just talking about the two levels, you have an additional level. For example, here there's a ground state, level 1, there's a next level 2, and then level 3, okay? So in this case, what happens is you create a pump to push electron or an atom from the ground state to the third level, okay? And then it undergoes thermal relaxation, and then it comes down to level 2. And now this is my lasing transition. The level 2 to level 1 is basically a lasing transition. And then this is my initial excitation, and then there is a non-radiative relaxation here. So when you have a scenario like this, it turns out that you can create, you can engineer, or you can try to find states which have a very, very long lifetime in the level 2. Okay, this will have long lifetime. If it has a long lifetime, that means atoms will stay in that state for a long time. So that's a very good condition for creating population inversion. Okay, so typically in our practical examples, we'll see these names thrown around. So I just wanted to introduce that. Okay, so you can have this long lifetime states, and of course, compared to a 3-level system, 4-level system is even better, because in the case of a 4-level system, I'll have my ground state, which excites to a higher state here, pump state, and then relaxes down. The electrons will stay in this, and I'll also find a level 2 state which is having very, very fast non-radiative decay. Okay, so basically I'll try to accumulate N2 and empty. Okay, not N2. I'll say accumulate try to have more number of atoms in this state E3, and this is E2, empty E2. Try to always quickly take out the atoms in the lower state. So in this, between these 3 and 2, you can have a lasing. Okay, so it's something like you are having, let's say, think of some sort of a emission. Let's say you have, think of these levels as tanks. Okay, the ground level is basically the basement tank, and the upper level is this. Now you want to have, let's say, 2 points between which you want to have, let's say, a fountain or something like that. You have to create a situation in such a way that the fountain is being pumped by, let's say, the level 3 here, and the water is getting accumulated in the level 2. So you quickly make sure that the level 2 is empty so that the population inversion is maintained. N3 minus N2 is always maintained, and then you have lasing. All right. So this is an interesting idea which is very, very important, and I think I don't want to spend too much time on this. So if you have questions, let's have an interactive session and we'll talk more details about it if you have doubts. But this is an important feature of lasing. Okay. All right. This is a quick overview of that. And so this is we have looked at what the cavity is. We looked at what the gain medium is. And one of the ways to create population inversion in semiconductors, in modern lasers, is by using what are known as double heterostructures, wherein I'll sandwich high, we talked about heterostructures, or quantum wells, wherein you had one gallium arsenide, let's say, sandwiched between 2 gallium aluminum arsenides on both sides. So there's a band gap change, and electrons can be injected into this region, and then the holes also can be simultaneously injected. So in this heterojunction region, we have simultaneously very large number of electrons and holes. So that is what we what we call as gain. Basically, you're creating gain that way, and you have a strong emission of photons. Okay, so this is a practical way of actually creating lasers. Okay, I know I've not spent too much time on this, but you can look up. This is a figure from, I think, Neiman. You can look at any standard textbook and you'll find the details on this. The essential idea is that you have a gain medium, which is created by this heterostructure. And then the cavity in the case of semiconductor lasers is actually created by cutting the wafer. Okay, in this case, this is you cut the interface, okay, very sharply, and the sharp interface itself will act as a mirror. You don't have to put additional mirrors, so that will actually cause lasing to happen. So these are known as diode lasers, which are very, very important for current technology. All right. So this is the overview of the basic processes involved in active metamaterials. So I'll stop here for this lecture. And in the next lecture, I'll talk about some examples of how these things actually will be useful and why we need to miniaturize lasers and so on, how they can help. So we'll discuss that in the next lecture. All right. So thank you very much for your attention. I'll see you in the next lecture.